Reverse engineering GenAI and the software team of the future. The other day, I came across a picture on LinkedIn that instantly grabbed my attention. It was a meme of someone looking completely baffled. Caption it, me debugging a generative AI model after I tried to get into the GenAI hype. At first, it seemed like a funny poke at the generative AI craze, but it resonated with me on deeper level. Everyone is eager to jump into the GenAI bandwagon. But that picture made me think about something that's been on my mind for a while. Reverse engineering. I've been wanting to produce a content about this ever since I explored the XZ backdoor attack in a video I published last April. The XZ backdoor was particularly intriguing because of how Andres Freund uncovered it. His investigation was a masterclass in reverse engineering. The complexity of the case and Freund's meticulous strategy sparked my curiosity about the techniques involved in such investigations. It also highlighted the fundamental truth. Reverse engineering and debugging are essential skills in every software engineer's toolkit. As generative AI models grow more sophisticated, mastering the art of debugging and reverse engineering their outputs is crucial. In today's video, I will explore these fascinating techniques and their applications in uncovering hidden threats like the XZ backdoor. The XZ backdoor, by the way, is a security vulnerability found in the XZ compression tool, which is trusted by countless systems around the world that use it for file compression and decompression. This backdoor gives attacker a way to execute arbitrary commands on systems running compromised versions of the software. By exploiting a flaw in how the XZ tool handles specific inputs, attackers can gain unauthorized access or control over affected devices. You can watch more about it here. The software team of the future. Debugging and reverse engineering in the GenAI era. The landscape of computer science is on the brink of a revolutionary change. The rise of large AI models like ChatGPT is transforming how we approach general-purpose reasoning and problem-solving. Experts like Dr. Matt Welch, who has an impressive background with Fixie AI, OctoML, Google, Apple, and Harvard, predict that the future of software development will look radically different. Traditional coding might become a thing of the past, with AI models taking over most software tasks. According to Dr. Welch, and supported by recent research into the cognitive and task execution capabilities of large language models, the software team of the future will look something like this: an AI robot code monkey generating code, a human product manager guiding the vision, and a human code reviewer ensuring quality and accuracy. This exciting shift promises to redefine the roles and dynamics within software teams, making it an intriguing time to be part of the tech world. Let's explore what this means for the future of software engineering. Debugging and reverse engineering in the GenAI era. As we edge closer to this AI-driven future, the role of the human code reviewer becomes more crucial than ever. Ensuring the quality and security of AI-generated code will demand expertise in debugging and reverse engineering. These skills have always been vital for software engineers. But in the GenAI era, they take on a whole new level of importance. Here is why. Ensuring security. AI-generated code might have hidden vulnerabilities. Reverse engineering helps uncover and fix these issues before they can be exploited. Understanding functionality. To grasp how AI-generated code works, reverse engineering provides insights into its logic and flow and makes maintenance and improvement easier. Compliance and standards. Ensuring the code meets industry standards and regulations is crucial, especially in sensitive sectors like healthcare and finance. Accuracy. Verifying that the model produces accurate and reliable outputs is paramount. Bias detection. Identifying and mitigating biases in the model ensures fairness and equity. How to debug a generative AI model? Debugging a generative AI model isn't too different from traditional debugging, but it does come with its unique challenges. Here is a breakdown of the process. Understand the model architecture. Familiarize yourself with the architecture of the AI model. Knowing how the model is structured, including its layers, parameters, and training data, is the first step. Monitor outputs. Keep an eye on the outputs the model generates. This includes both the correct and incorrect outputs. By comparing these, you can start identifying patterns in errors. Trace data flow. Track how data moves through the model. This can help identifying where things go wrong. Tools like TensorFlow Board for TensorFlow models or PTorches inbuilt visualization tools can be immensely helpful. Analyze gradients. Investigate the gradients to ensure they are flowing correctly during the training process. If the gradients are too large or too small, it can indicate issues like exploding or vanishing gradients. Test with known inputs. Use test cases with known outputs to see how the model performs. This can help isolate where the model starts to deviate from expected behavior. Iterate and refine. Debugging AI models is often an iterative process. Make changes, retrain the model, and test again to see if the issues are resolved. 5 must-known reverse engineering and debugging techniques. While the techniques mentioned earlier are crucial for tackling GenAI code, there are fundamental practices every software engineer should master. Here are 5 essential techniques that will elevate your reverse engineering and debugging skills. Static analysis. This technique involves examining code without running it. Tools like IDA Pro, Ghidra, or Radar 2 can disassemble and decompile binaries. They offer a clear view of the code structure and spot potential vulnerabilities. Dynamic analysis. Unlike static analysis, this method requires running the code and observing its behavior. Tools like OllyDbg and WinDbg are great at understanding how the code interacts with the system and identifying runtime issues. Binary diffing. This powerful technique compares different versions of a binary to highlight changes, making it invaluable for detecting patched vulnerabilities or modifications. Tools like bindiff are perfect for this task. Log analysis. By scrutinizing logs generated during program execution, you can trace the flow of operations and pinpoint where issues arise. This is especially handy for debugging complex systems. Fuzzy testing. This technique involves bombarding the system with random data to see how it handles unexpected inputs. It's an excellent way to uncover hidden bugs and vulnerabilities. Case study. Andres Freund's methodical approach in exposing the XZ backdoor. Let's dive back now into the intriguing XZ backdoors case study. In March 2024, Andres Freund uncovered a major security breach in the XZ utility, a popular data compression tool. Freund's discovery was nothing short of groundbreaking for the cybersecurity community. Through a meticulous blend of reverse engineering, debugging, and expert software engineering techniques, he was able to identify and diagnose the XZ backdoor. This was a critical step in preventing potential global security disasters. So how did Freund do this? Based on his details emailed to the OSS security mailing list, here is a breakdown of his methodical approach. Initial detection. Freund noticed several odd systems, such as high CPU usage. SSH logins were consuming more CPU resources than usual. Valgrind errors. The memory analysis tool Valgrind reported anomalies during SSH operations. These anomalies prompted a deeper investigation into the libeltzema library, which is part of the XZ package. Reverse engineering and debugging techniques. Binary analysis and tarball comparison. Freund compared Debian's imported tarballs of XZ with the official upstream source code. He found differences indicating that the distributed tarballs has been compromised. The compromised turboles contained an obfuscated script executed during the build process, which injected malicious code. Dynamic analysis. He used GDB GNU Debugger to analyze the runtime behavior of the backdoor. By setting breakpoints, he traced the execution flow to identify where the injected code was triggered. Front used perf record -e until pt/app/ub to observe execution divergence between normal and compromised states. Deobfuscation. The backdoor's code was heavily obfuscated to avoid detection. Front deobfuscated the injected script and the resulting modifications to the makefile. The script altered the build process, embedding a hidden backdoor that activated under specific conditions. Function interception. The backdoor intercepted execution by replacing the ifunc resolvers CRC32 resolve and CRC64 resolve with malicious versions, enabling it to execute its payload early in the startup process. Front observed that the backdoor modified symbol tables and installed an audit hook in the dynamic linker to manipulate function pointers. Reproduction and testing. Front replicated the condition under which the backdoor activated, such as specific environment variables and build configurations, to consistently trigger and study its behavior. He tested different scenarios to see the impact on SSH, confirming that the backdoor could slow down or manipulate SSH logins. Analysis and reporting. Front's thorough investigation revealed the intricacy of the XZ backdoor, injection mechanism, an obfuscated script in the build turboles modified the build process to include the backdoor. Targeted conditions. The malware is activated under specific conditions such as building the GCC and the GNU linker. SSH compromise. The backdoor affected SSH logins by redirecting critical functions to its own code, potentially allowing unauthorized access. Impact and recommendations. Front's meticulous work and proactive measures prevented the widespread exploitation of the XZ backdoor. His findings highlight the critical importance of vigilant monitoring, detailed analysis, and collaboration in cybersecurity. The exploration of reverse engineering and debugging in the context of the XZ backdoor case illuminates the broader significance of these keys in an AI-driven future. As AI models like ChatGPT take on more software tasks, the role of human engineers will evolve to ensure the robustness, reliability, and ethical standards of AI-generated code. Mastering reverse engineering and debugging is not just about security. It's about understanding and refining the complex outputs of AI, maintaining high standards of functionality, and ensuring compliance with industry regulations. In the future software team, the collaboration between AI tools and human expertise will drive innovation, solve complex problems, and push the boundaries of technology. By honing these critical skills, we can navigate the challenges and opportunities of the AI-driven future. Keep pushing forward, and happy coding. That's it for today. If you liked the video, don't forget to hit the like button and subscribe to the channel. And see you next time.